The last piece to the gas chromatograph that we're going to look at in these videos is the variety of detectors that we can have for GCs. Now, there's a whole range of different detectors out on the market, and I'm just going to highlight a couple of the most common ones here. The first type of detector that we'll look at is a thermal conductivity detector. And this is abbreviated a TCD. So if you see something that's a GC-TCD, that's a gas chromatograph with a thermal conductivity detector. Now, what does this do? Essentially, you have a heated block, okay, and inside that block, let's draw a heated block. A little in point where we're going to send our eluent. Remember, this is what's coming in from the column. And then we need a kind of a block area for our eluent to come out. And so this is a heated area here, a heated block. Here's your heated block. Okay, so this is heated, and inside this block there is a hot filament. I'm just going to draw this filament like this. And we have a hot filament. So what happens here? Okay, the hot filament is actually going to be measuring kind of the heat in this TCD detector. Now, the entire premise is that as your analyte comes in and passes out, it can absorb some amount of heat, okay, or block the heat, right? So we're looking at how does the analyte transmit heat. And if this analyte passes, we get kind of a decrease in conductivity of this filament based on the heat. So it's the conductivity of this filament is heat dependent or temperature dependent. So if the analyte comes in and starts absorbing the heat, then as the heat is absorbed, the temperature in this chamber drops and our filament's conductivity is going to change. By measuring the continual conductivity of the filament, you will see a change in the conductivity as a function of the number of analytes passing through the detector. So more analytes that absorb heat equals reduced conductivity of the filament. And that reduced conductivity of the filament is what we ultimately measure in terms of our detector. So when we think of the specificity of this detector, this can't tell us exactly what analyte is eluting. It can tell us what time it eluted from the column at based on the signal, but it can't distinguish necessarily between one analyte and another. So the selectivity of it is, in terms of giving us additional information, is not great. And we'll see that with several of our GC detector types here. But one thing that is true is that we get very good sensitivity at very low flow rates, okay? And also when you're at the maximum temperature difference between the filament and the heat block. So we have to keep this hot enough to keep the analytes as gases, so that as they're passing through, they're not also condensing. What are the advantages of this? Well, this is a pretty simple detector. It responds to all of the analytes. It does not alter the analytes, so you could still put it through the thermal conductivity detector and then ultimately try to collect it or use another type of analysis after this detection technique, because we haven't changed the analyte in any way. All it did was absorb some heat. One of the disadvantages that even though it can have good sensitivity at low flow rates, it's still not very sensitive in terms of overall detections. So there's some advantages in its universal response, but a disadvantage in that it has a very low sensitivity compared to other options. All right, so our next detector type is a flame ionization detector. This is abbreviated in FID, so if you see a GCFID, that's a gas chromatograph with a flame ionization detector. Okay, in this case, we're going to essentially burn the eluate in hydrogen gas and air mixture. Okay, so we're going to do combustion. Okay. And so what we're ultimately doing is, in the combustion process, carbon atoms produce CH radicals. And as these CH radicals are produced, in forming radicals, we also form free electrons. Okay. Those free electrons are going to go from form a constant current from the flame that's burning these eluates to an electron collector or a cathode. Okay? By measuring the voltage applied at that cathode and the change that comes from these free electrons forming, we get a nice signal from the free electrons. So what we're ultimately measuring here is the electrons formed in this detector. So what are some advantages of this? Well, we get a wide response range. We can see across about 7 orders of magnitude of concentration, which is really pretty cool for these instruments to be able to get that wide of a response range. But the detection limit is actually low. It's about 100 times lower than TCD. I guess that's not a but, that's an also, right? That's an advantage. So it's about 100 times lower than the TCD. So we're much more sensitive with the flame ionization detector than we are with the thermal conductivity detector. However, one of the disadvantages is that we can really only detect hydrocarbons. So if you're looking at something that's not hydrocarbon based, we can't do this carbon atom into CH radical formation, and so a flame ionization can't be used for non-hydrocarbons, which can be a big disadvantage. So this is one that's really commonly used for arson analysis, because most of your ignitable liquids in an arson analysis, which is what you'd be looking for, are actually hydrocarbon based. And this is a fairly inexpensive instrument in terms of GC instrumentation. All right, the next type of instrument detector here we're going to look at is an electron capture detector. And this is abbreviated ECD. Okay, so you notice we have a variety of different abbreviations. So when you're purchasing an instrument, always make sure you know what kind of detector you're getting with these GCs and that it's going to do what you want it to do. Okay, so how does an electron capture detector work? So just as the name applies, we're going to need a kind of field of electrons that our analyte is going to capture from. So here we go. We've got a sketch here Okay, I've got somewhere for my eluent to go in, somewhere for my eluent to come out. Okay. I'm going to put an anode in the top and a cathode here at the bottom. So what happens between the anode and the cathode? With a cathode and an anode, when they're connected and you've got this kind of voltage applied, okay, what you end up forming is an electron cloud between them. As the electrons jump from the cathode, from the anode to the cathode. So as they pass between these two electrodes, we get an electron cloud. And then when the analyte passes through, if your analyte can pull an electron, okay, we need an analyte with a high electron affinity. And they're going to pull an electron from the cloud. What does this do? Okay, when we pull it from the cloud, now the number of electrons passing back and forth between the anode and the cathode is decreased. So we ultimately get a decrease in signal from the electrons in the cloud. And that's what we're detecting here. We're looking for a decrease in signal that is detected. Now because we need analytes with high electron affinity, this makes us a very specific kind of detector. It's not universal like we saw with the thermal conductivity detector, where this could analyze just about everything. The flame ionization could analyze hydrocarbons really well, but the ECD now looks at analytes that have high electron affinity, or groups with halogens or conjugated groups like carbon, like ketones or cyanide groups or nitrate groups attached. Okay, so all of those are structures that are going to have very high electron affinity and are going to be especially good for this. So an advantage of this is that it's very specific to our things, and we get very good sensitivity, better even than the FID for those types of analytes. But a main disadvantage is that it's very specific. You can't analyze everything with it. It has to be analytes with high electron affinity in order to actually see any kind of detectable signal. So this can be a good thing, but it can also be a pretty bad thing. If you're trying to analyze, say, hydrocarbon-based analytes, you wouldn't want an electron capture detector because it's not going to get very good signal at all for these these analytes without high electron affinity. All right, the last type that's of detector that's very commonly used with GC is mass spectrometry. And we'll spend a whole 2-week module on this, and there's a whole course on mass spec. If you haven't taken it already, I encourage you to take that in the spring. But for mass spectrometry, we will talk about this in its own right. But what I want you to know for this portion is that this is a universal detector. So much like with thermal conductivity, we can detect pretty much everything by using mass spec. The other main advantage of mass spec is that in getting the signal, it's going to give us structural information. So mass spec is a technique, a standalone in its own right, but when paired with gas chromatography, this can be a really powerful system to use as a detector. Okay, so those are our 4 main types of detection systems that you'll see with a GC. You might see it as a GCMS, GC-ECD, GC-FID, or GC-TCD. Okay.